Hello, so welcome. In this video I'm going to do something a little different from what I usually do. Instead of solving problems, I'm going to present to you a small algorithm here, a flowchart that I've created to help you solve most of the first order ordinary differential equation. Now, a disclaimer here, the methods I'm going to present here do not necessarily solve all the first order ordinary differential equation, but for most of the questions you will meet in the papers or exams, these methods should be able to help you in the order that I've actually arranged them. So these methods are only applying to mostly first order ordinary differential equations. So the first question you usually want to ask yourself if you have a first order ordinary differential equation is if the differential equation is simple separable. Now, if the differential equation is simple separable, that's the simplest method of solving all differential equations. Go ahead and separate variables, integrate both sides, and there you have it, the solution. If it's not simple separable, then the second question you want to ask yourself is if the differential equation is exact. Now, I'm giving you this algorithm because I don't want you to kind of go to the very abstract methods, yet the equation can be solved by simpler methods, alright? So if the equation is not simple separable, then try to check if it is exact. Exact means you can express the left-hand side of this equation as an exact differential, using product rule or quotient rule. So if it's an exact differential equation, then you go ahead and form the exact differential on the left-hand side or right-hand side for that matter, and then you separate variables and then you solve that. All right, so sometimes it's not an exact differential, but still you don't have to think so much outside the box. You can first see if the equation can be made exact by multiplying it with an integrating factor. Integrating factors are very important when it comes to differential equation. In fact, most problems you will meet will actually require you to use an integrating factor. So if you find that the differential equation is not exact, sometimes it's easier to make it exact by using an integrating factor. There are two things involved here if you are to use the integrating factor. The first one, if the differential equation is first order linear, then just express it in this form, the so-called normal form. You just divide by the coefficient of dy dx throughout the equation and just express it in this form, and then find the integrating factor using this formula. I guess you've looked at this, it's a very common one. Then if you multiply by the integrating factor, the first order linear differential equation will become exact, and then you can now separate variables after combining the exact part. So if it's not first order linear, still you can sometimes find the integrating factor by inspection. The method of inspection or analysis works for all first order differential equations that can actually be made exact with an integrating factor. So you may also want to check that out and see if you can find the integrating factor by analysis. I will leave a link in the description to a playlist where I actually talk about all these methods of solving first order differential equations so that you can actually look at them. Now, if the differential equation cannot be made exact either by multiplying it with an integrating factor, then the next question you want to ask yourself is if the differential equation is homogeneous. Homogeneous in a sense that all terms have the same dimensions. And if they have the same dimensions, then it means we can use the substitution y equals vx or ux, depending on what your teacher calls it. So this special substitution makes the differential equation in most cases to become simple separable so that you can easily solve it. That's if it is homogeneous. So if it's not homogeneous, then most probably it is a Bernoulli equation. As you can see here, I have a general form of a Bernoulli equation, dy dx plus py equals qxy to the power n, where n of course is greater than 1. And for the Bernoulli equation, we have a special substitution, z equals y to the power 1 minus n. And if you apply this and substitute for dy dx, it's kind of changing the variable. You will get a linear differential equation which you can solve using the methods we've just described above. And if the first order differential equation you're looking at does not match any of the methods we've looked at, probably it takes up another special form and can be solved by another, special substitution which is not generalizable. And usually that substitution will be given to you in the question or the problem you're trying to solve. Of course, I also must say that not all differential equations have analytical solutions. Some differential equations cannot be solved analytically. That's why we have the Euler methods and the Runge-Kutta methods, and that's how calculators and computer softwares like MATLAB, Wolfram Alpha, Mathematica, that's how they actually solve these equations most of the time. Alright, so thanks for watching this video. I hope these methods become super useful. I know these methods are, just the basics. They don't solve all the first order differential equations, but at least I know they will be a little helpful in giving you the basic ideas of the, common methods of solving first order differential equation. Thanks for watching. See you in my next video.